So chapter 16, which talks about rigid bodies and involves rotation, you will realize that is the fundamental part of your dynamics analysis. For those who are ME, which I think most of you are ME or maybe MRE, if you go to mechanisms, half of it is still just this chapter 16 with little extensions, okay? If you want to do robotics, if you want to design any machinery, it requires, I mean, robotics is more advanced because chapter 16 is two-dimensional in-plane motion. Robotics is three-dimensional, so it makes it quite more complicated. But the core part of your dynamics knowledge as a mechanical engineer is this chapter. It's a longer chapter, and I may assign more than 6 homework problems, okay, because I want you guys to be exposed. I suppose you do the others that are not, you know, forced to be submitted, but it's still, I may give you a couple of more problems, maybe 8 or 9 for this chapter, so we can cover different bases and you're exposed to enough material. With that explanation, let's just go and share the screen. Last time we did this problem, and now, if you recall, we talked about translation only and rotation only. For translation only, we learned that the motion of the rigid body can be expressed by single point because it's not rotating. Every point technically has the same velocity. For rotation, we develop equations for omega and alpha as angular velocity and acceleration. We developed vector equations to analyze velocity and acceleration of the point on a rigid body. And we realized that for a rotation only, you have usually a normal acceleration, a tangential acceleration. One of them could be 0, either of them, right? But if both of them are 0, technically there's no acceleration. Now, we talk about general motion. When we talk about general motion, as we discussed before, the object, the rigid body, undergoes translation and rotation at the same time. I don't know if you can see my hands here, but if this is the case of my glass, this is translation, right? No change of angle. This is rotation. If I hold it here and just rotates, general motion is when things move around and change angle. So in that case, you have a combination of translation and rotation. Now, to analyze this, we have 2 approaches. One, we call it absolute motion analysis, and one, we call it relative motion analysis. You're going to see shortly how these names are selected. For absolute motion analysis is pure geometrical, which means it's kind of similar to constraint motion that we had in chapter 12. You find equations that relate geometry of 2 points, right? In chapter 12, the 2 points were 2 particles. Here, the 2 points are on the same rigid body. And I know this kind of looks confusing. I'm going to explain it later in detail. In relative motion, we use vector analysis, which has 2 approaches. We're going to talk about that later. Now, as I said, in absolute motion analysis, we relate geometry of the system to particular points on a rigid body, and we create like L equals sine theta, L equals cosine theta, for things like that, right? When theta is angular position, L or X or Y or S, these are linear displacements or positions. So technically, your displacement somehow is function of theta. What this function is, it depends on the geometry. When you take the time derivative of displacement, S dot, which is velocity of that single point, creates a function based on theta and theta dot. And when you want to find acceleration, when you have S double dot, you take the second derivative and you're going to get functions that has theta in it, sine theta, cosine theta, tan theta, those parameters. Then you have theta dot and theta double dot. So technically, from the geometry, you can relate velocity and acceleration of a point to angular velocity and acceleration. So is the general concept clear? This is still confusing, I understand, but let's just do an example and see how this works. We may have done something similar to this in chapter 12, when point B is one particle and point A represents another particle, these two sliders. Is it still the same thing? B represents this slider and A represents this slider going horizontal. But because A and B have a shared point on this link AB, we may consider this rigid body AB as my object. So the problem says 2 meter long bar. So this is 2 meter. It's confined to move one edge horizontally, one edge vertically, right? The velocity of a slider is given 8 meters per second. You want to find, excuse me, the angular velocity of the bar and the velocity of B when theta is 60 degrees. Now, when I solve this problem, you understand those function of theta and stuff like that. I give you a few seconds to draw this. Excuse me. So to solve this problem, as I said, we need to relate position of A and B and angle theta. Okay. If I want to do that, how do you think I can do it? How I can relate theta to the position of A and B? Any suggestion? So let's go to the tablet, show you how it looks like. So this is how the problem looks like, right? The problem says A has a velocity of VA going to the right. And let's say I want to consider position of A. This is my reference for position of A. I'm going to call this as XA. And let's say this is the reference for position of B, because B just goes up and down. Its Y changes, so this is YB. Okay. How I can relate position of A and B and theta using this geometry. Remember, theta is 60 degrees, but the equation we develop is general. Any suggestion? Does this triangle remind you anything? Hmm? Haoshin, this triangle, how we can relate XA, YB, and theta using this triangle?
XA to order plus YB to order equal 4.
Okay, we can do that, right? That's a good observation. But remember, we are looking for VB and omega. Not that this is wrong. We need two equations, okay? You can use this equation, take the derivative like 2xa, xa dot plus 2yb, yb dot equals 0 because L is constant. And then you calculate yb dot from here and go forward. And that's completely fine. We can continue to calculate this. Then we need to find something that has theta in it. So for me, because I'm lazy to take these derivatives, I'm going to go xa equals L cosine theta, yb equals L sine theta. You could use this equation that Haoshin said, and one of these equations. That's still fine. Because remember, two unknowns, two equations. This could be number 1, this could be number 2, or this could be number 2. Doesn't matter. But I chose to go with x and y and cosine theta and sine theta. So everything is like in trigonometric form. So you remember in the previous slide, I said you find S as a function of theta, and then S dot becomes df d theta, theta dot, and then S double dot. You continue, same thing. Technically, this is your F theta. Let's say F1 theta. And this is your F2 theta. Y is a function of theta. X is a function of theta. You got it from the geometry of the system. And that is what we call it absolute motion analysis. Kind of goes with constraint, okay? Now that we have these functions, we're going to do these derivatives. If I do the time derivative, let's call this equation 1 and this equation 2. Time derivative 1 gives you xa dot, which is VA, is equal to L minus sine theta, theta dot. And equation 2, YB dot, which is VB, L cosine theta, theta dot. Is it correct? Remember, we don't go with when we talk about VA, and please take the note for this comment. When we go for VA and VB, because they're the time derivative of this value, the X and Y doesn't mean anything, right? If XA becomes larger, then VA is positive. If XA becomes smaller, then VA is negative. That's how negative positive works. Like, for example, here, VA, as A goes to the right side, XA becomes bigger, so VA is positive. That's how we do it, okay? So if I substitute the values for 1, I'm going to get 8 equals 2 times minus sine 60 theta dot. Remember, theta dot, change of this angle is the definition of omega, right? Is it or is it not? This theta dot, when this goes here, you have an omega of theta dot going this way. So this is technically omega. I'm going to put the omega here. Same for omega. Because this is the change of theta, we don't go, you remember we said omega is a vector. If we go with right-hand rule, the rotation and x and y, here again, theta dot is the change of theta, which means theta getting smaller, theta dot is going to be negative. And you see here, as A goes to the right-hand side, theta becomes smaller, so we expect a negative omega. Although if you use the right-hand rule, it goes to the positive k, but this is not vector analysis. We don't care about ijk. That's what we call it, absolute analysis, okay? Now from 1, you can get your omega is 8 divided by 2 sine 60 with a negative. How much is this number? You guys give me the number.
I got negative 4.62.
The unit,
Is it radians per second?
yes, because it's angular velocity, right? And then we're going to go to equation 2. Then you get VB is equal to L cosine theta, which is 2 cosine 60. And this should be theta dot here. And theta dot, which is omega, is going to be minus 4.62. And if you calculate this, VB is going to be minus 4.62, same number. Here, the unit is meter per second. Okay. So that is how you connect or you relate x's and y's or s's, the displacements of 2 points, usually 2 points on a rigid body, to the angular position, displacement, velocity, acceleration. And when you construct that geometrical equation or equations, depend on, you know, how many parameters you may have, then you can just take the time derivatives and get the values. Again, remember, positive and negative here does not correspond to positive x and y. This is not a vector analysis. There's no like ijk things, right? Positive and negative means if the magnitude of that parameter, if it's x or y or s or theta, if it gets bigger, its time derivative will be positive. If it's a smaller, its time derivative will be negative. Okay? The problem does not ask for acceleration, but if you want to find the acceleration, let's say the problem says omega is constant. Now I'm extending this problem, okay? Make it, like part B now. Just follow here. If omega is constant, oh sorry, omega cannot be constant because the V is the input. Sorry. If VA is constant, find acceleration of B and alpha angular acceleration. Okay, remember, look at here for a second, please. Just because A has a constant speed doesn't mean B also has a constant speed or omega is constant. Because you have sine, cosine, theta, it is usually not the case. It could be at a certain moment when theta becomes sine theta or cosine theta becomes 0, one of them becomes constant. But please do not make this mistake, because V is constant, nothing else should be constant, literally. Okay? So we can go and find velocity and acceleration. Any question about this concept? Are we good? If I give something like this as a quiz, can you do it right now? I'm going to ask the majority. Kelly, if I give something like this as a quiz, can you do it right now?
I feel like I would need some practice at it, but
The concept is obvious.
Yeah.
Same for everybody. Okay. So I'm not expecting teaching you something and in the 30 seconds give you a quiz, but when you think about this to see, can you grab the concept and move forward? Of course, you need practice because not every geometry could be sine and cosine like this, could be different, but we're going to go back to the velocity terms. VA was, what was it? Minus L sine theta, theta dot, and VB was L cosine theta, theta dot. These are the same as, you had like S dot equals DF d theta, theta dot. This is the same thing. And I can simply substitute theta dot with omega because we know that it's the same. So just get used to use omega. Which omega? Omega of link AB. You can put AB here. You don't have to because we have only one link. But this omega is omega of link AB. You see this link? This link AB. Oops. Omega is for this rigid body. It goes like this. Okay. Now, to find accelerations, we're going to take the second time derivative here. Again, time derivative of, this is equation 1, 2. Now, you guys know how to do the time derivatives. We have done something similar to this in chapter 12. I'm going to give you 2 minutes to complete the time derivative of these two equations. You can do the number one first, and then go for number 2. Okay. So equation 1 The time derivative of VA is going to be AA. Here you have minus. The time derivative of sine is going to be cosine theta times omega. And then you have another omega. It's going to be omega squared. Then you can put it this way because minus L is constant. Then the time derivative of the second plus sine theta, the time derivative of omega is going to be alpha AB, right? Technically, this is theta dot square, and this is theta double dot. And if you go equation 2, we're going to get AB equals L minus sine theta omega AB squared plus cosine theta alpha AB. Okay, again, this is theta dot squared that comes from the derivative. This is theta double dot. We have done something similar to this in chapter 12 and for other purposes. Okay, any question? Okay, now I'm going to go back to equation 1. Because AA is 0, A is constant, so from equation 1, you can simply get minus L cosine theta omega AB squared plus L or minus, sorry, minus L sine theta alpha AB equals 0. I'm going to take alpha AB term to the other side, and you can cancel out L values, right? Therefore, you're going to get alpha AB is minus cosine theta omega AB over sine theta. And considering theta was 60, you have minus cosine 60 over sine 60 omega AB, which was minus 4.62. Was it? Yeah. Which means your alpha will be positive. And it's going to be 2.667 radian per square second. Did you guys get the same number? And if I want to go with equation 2, AB, I'm going to substitute the values. 2 times minus sine 60 4.62 square plus cosine 60 times 2.667. And someone give me this number, please. This is too long for me to calculate. Okay.
I got negative 34.3.
33 point.
34.3, negative 34.3.
meter per square second. Anyone get something similar? I think you're right with the number. I didn't finish, but I got close to this. So that is how you use the absolute motion analysis to be able to solve a general motion problem. Remember, are you guys done writing? Now, look at this. If this was the slider, right? Technically, B and A are two rigid bodies having linear motion or translational motion. But as this goes down, you see, even if it goes here, so your link AB has this general motion, a combination of translation and rotation. And that's how you can analyze this problem. Okay. Let's go back to the slides. And do one more example. This is another example. It says you have like a hydraulic cylinder here, hydraulic jack. It pushes the point A vertically up and down, right? Point A is connected to two rigid bodies, OB and AB. And as you see, OB and AB have the same length. So you have certain geometry here. The problem says when Y is 200 millimeter, which means you're going to get 60, 60, 60, oops, angle. But that's general, right? At that particular moment, pin A has angular velocity of Y dot 400 millimeter per second, which means if 400 is positive, does A go up or down? If Y dot is positive, that means A goes up or A goes down. Aaron, based on what I explained, when Y dot is positive, does it mean A goes up or A goes down?
A goes up.
Goes up. If A goes up, does length of Y becomes smaller or bigger?
From smaller.
Smaller. If Y becomes smaller, its derivative is positive or negative?
Negative.
Negative, huh? You see, that's a good mistake to make, so it reminds everyone. Remember, I mentioned a few times, Y dot and Y double dot don't go with XYZ thing. Because you take the time derivative of the geometry, this becomes bigger, this is positive. This becomes smaller, this is negative. Same thing with theta. Theta becomes bigger, positive. Theta becomes smaller, negative, right? So it gives all the numbers for A and wants you guys to find omega and alpha of link AB. So technically, we have to relate this Y somehow to the angular position of link AB. And to do that, let's go to the slides, to the tablet. So this is the point where A and B, A moves on, right? And you're going to have something like this, and then something like this. This is that position, but we write the equation. Remember, we don't write it for single position. We write it as a general point. So this is O, this is B, this is A, and A, based on what we have got from the problem, which says this is Y, A goes down, right? The length of everything is given. This is, let's call them, this is L. This is going to be L2. And this angle, I'm going to call it theta. Why I picked this angle? Because this angle could show me the angular position of link AB, right? Now let's write down the numbers. So we have theta at that moment is 60 degree. Oh no, sorry, it doesn't say theta is 60, it says Y. Y is 200 millimeter. L is 200 millimeter. Y dot is 400 millimeter per second. And Y double dot is minus 100 millimeter per second square. Okay. We are looking for omega AB and alpha AB. Now, look at this geometry here for a second. How I can relate Y, because remember, Y is the input of the problem, right? Y is what I'm given. How I can relate Y to theta using this geometry. Any suggestion? I'm going to give you a hint. If I draw a line here, how much is this length? How much is that length? Come on, guys. If the whole thing is YA, how much is this?
That half of Y.
It's half of Y. Why? Because this and this are the same, right? If they were not same, you have to find another equation. But because OB and AB are the same, so this is technically YA by 2. Now that you know that's YA by 2, let's go to this triangle, right? And see how I can relate theta to YA. Any suggestion? Jake Z. Let's ask Jake Z. Sorry, I cannot pronounce your family name properly. I don't want to embarrass myself. I'm just going to go with Jake Z and Jake B.
Yeah, it's kind of a hard one.
Yeah.
What was the question?
The question is how I can use this triangle and relate YA or YA by 2 to theta.
Wouldn't it just be tangent or cosine of theta is equal to YA divided by 2 or over L?
Yeah. So technically, YA by 2 is equal to L cosine theta. And that is, or technically YA is 2L cosine theta, right? This is my S equals F of theta equation, right? From here, you simply take the time derivatives, and I'm going to give you 1 minute to get, technically, if we do the time derivatives, and this is equation 1, then you're going to get y dot A equals something, and y double dot A equals something. I want you to do this and tell me what to write. 1 minute. Get it? So the first one, you're going to get 2L minus sine theta, theta dot, and we know that theta dot is going to be omega. So you're going to get 2 minus 2L sine theta omega AB. And if you do the derivative of this, you're going to get minus 2L cosine theta omega AB square plus sine theta alpha AB, right? Equation 1 and 2. Or if this is 1, let's make this 2 and 3. 2 and 3, this is 1. Okay. Now from equation 2, your omega AB is going to be YA dot over minus 2L sine theta. How much is theta? The problem says when YA is 200, right? YA is 200 and L is 200. So this, and this are the same. What do you call this triangle? Come on, guys. Triangle with equal sides. Are you lazy or you just don't listen? Or maybe you're watching YouTube stuff or TikTok on your
It's an equilateral triangle.
equilateral triangle. Equilateral triangle, how much is theta?
60.
60. So at this particular moment that y is 200, theta is 60. So technically from the geometry, from this, you can consider that theta at this moment is 60. Now I'm going to put the values here, okay? This was, how much was y dot? 400. You get 400 divided by minus 2 times 200 times sine 60. So your omega AB, remember the units should be the same. This is millimeter, this is millimeter per second, so we are good. If that's the case, this 400 cancels this 400, so you're going to get minus 1.155 radian per second. Okay. Any question? Am I going too slow or too fast? Looks good. So the whole idea is to find that relation between an X or a Y or something and theta. And remember, I don't want to scare you, but if you cannot find that equation, you cannot solve the problem if you use absolute motion analysis, right? You have to get the right geometrical relation. Now we're going to go to equation 3. So for 3, you're going to get YA double dot equals minus 2L cosine theta or omega AB squared minus 2L sine theta alpha AB. So if I want to calculate this, I'm going to take this to the other side and this to that side. So you're going to get alpha AB over 2L sine theta is equal to minus 2L cosine theta omega AB squared minus YA double dot. Okay. I take this term to the left-hand side becomes positive. I take this to the right-hand side becomes negative. Then I divide the two sides by this. So this is what I'm going to get. And if you substitute the values, alpha AB is going to be minus 2 times 200 cosine 60 omega AB squared, which is 1.155. You see, it's negative, but because it's a square, I don't put the negative sign because it doesn't matter. Or you can put the negative sign anyway. Minus 100 divided by 200 times sine 60. Give me the number for this guy. This is too complicated for my iPhone. 1.155 squared. 16. You get the same number, 1.059, or do I get it wrong?
I got negative 0.48.
Like this? Okay, we have 1.155 squared times 60 cosine times 400. This gives me 266 something. Oh, okay. This should be negative. That's negative. Okay, I got the mistake. Minus 100. I think you got it wrong. Right. Divided by 400. Then divided by 60. Sine. Yep, 481. You're right, as always. Minus 4.482 radian per square second. Any question about these two problems? So again, I repeat, when you solve a problem using absolute motion analysis, and some of the homework problems are from that part of the chapter, and even I may ask you in the quiz or exam, solve this problem using absolute motion analysis, because there's other ways to do the technique we're going to talk in a few minutes. You can use that one too, right? The point is, when you do this, again, you find some x, y, s values. The geometry should tell you what to pick. And then relate it to the angular position of the rigid body. From there, it's just time derivatives. Something to remember, again, I repeat that V, A, omega, and alpha, they do not go with X, Y, Z, because this is geometry based. They go based on if theta becomes bigger, omega is positive. If theta becomes smaller during the motion, omega is negative. Same goes with VA or VB. Any X and Y become bigger, their X dot Y dot value is going to be positive. If they become smaller, the X dot Y dot value will be negative. Make sense? Okay. So that was the whole concept about this absolute motion analysis. In the next slide, we're going to start the vector motion analysis. So, which is relative motion analysis in contrast with absolute motion analysis. I'm going to give it like 3-4 minutes of break. You guys can come back at 11, okay? And we're going to continue the things. Just 5 minutes break for you guys, so kind of you relax between the two topics. Be back at 11. Any question about the absolute motion analysis? Is the concept clear? Remember, again, each problem, you need to understand how to relate the geometry, right? It's not always maybe sine and cosine like this, or something like this simple. It could be different. It could be simpler. Sometimes you need 2 equations. Sometimes, like the second problem, you need 1 equation. But if you look at the problem and a couple of things we did, right, examples, you may see the input and output are kind of telling you how to relate them, okay? It's usually through sine, cosine, but that's how it goes. Now, let's go with the absolute motion, with the relative motion analysis, which is a vector-based. I want you guys to pay attention to this rigid body's motion. You remember we talked about relative motion, 2 points, A and B. We use this for translation. RA represents the absolute vector position of A. And I'd say absolute vector means from a fixed XY coordinate system. X prime, Y prime, which is another coordinate system, is attached to A, but does not rotate with the rigid body, right? It just translates. RB is the absolute vector for B measured from this reference. And RB respect to A is the relative vector in X prime, Y prime coordinate system. Technically, I don't know how you can visualize this. Imagine you're sitting at the position of A. You don't see anything like this. You look at B, and this is what you see, right? Now, look at the animation. To find the velocity, you have to take the time derivative of this. RB, which is absolute position vector for B, RA is the absolute position vector for A, and RB respect to A, the relative position vector. Look at the animation. the particle, or the not the part, the rigid body goes from here to here. To move from this position to that position, it undergoes translation and rotation. I'm going to do it one more time. You may see X prime, Y prime, they don't rotate, right? They just translate. That's why we call it translating coordinates, because Y prime and X prime do not rotate. The rigid body has a general motion. And if you look at this, now let's see, this is the motion, how we can find the velocities. We take the time derivative of RB, RA, and RB respect to A. For this guy, this is going to be VA. For this guy, RA, DRA, DT is going to be VA. This is going to be VB. The question is, what is this guy? Now, there is derivation in the textbook. You can look at it. And there is this conceptual explanation. This is the motion of B respect to A, right? Which means you sit at A, what do you see? Let's just play it here. This is the original position, X prime, Y prime, and A. And this is the final position, right? If you are sitting at A, what do you see? One more time. What kind of motion you see?
Pivoting.
Pivoting, we use the word for it in this chapter. What we call this? Anyone else? Why Aaron is checking the notes? Colin, what kind of motion is this? Look at here one more time. Remember, you sit on A, so you don't understand, you don't feel your own motion, right? It's like you are in a bus, right? Bus drives with 65 miles an hour. You don't feel that, right? If someone walks in the bus, that's what you see. What you see if you are sitting on A attached to this coordinate system?
Pure rotation.
Pure rotation, or rotation about fixed points, right? So technically, from perspective of point A, what we see for B is just a rotation, right? With an omega. What was the velocity equation for velocity for rotation about fixed point? If you go back to your slides. Did you find the equation? You know what? I'm just going to go back and show it to you. For rotation about fixed point, what is the equation for velocity? Omega cross product R, right? So now that you are sitting on point A, and you see this motion, technically, if this is rotation about fixed point, this should be omega cross R, which R? RB respect to A, this R. And that is how you get the velocity of B using velocity of A and omega of the rigid body. Technically, you may say in general motion, I have a combination of rotation and translation at the same time, right? This vector shows the translation part. This vector shows the rotation part. Any of them that is zero, you simplify the case. When omega is 0, this is what we got at the beginning of the chapter, translation only. Every point has the same velocity. When A is a fixed point and doesn't have velocity, then B is rotation about fixed point. When both of them exist, you have a combination of translation and rotation. And that is how you can find your velocity equation. Does that make sense? Any question? Okay. Now that we have got this velocity equation, we're going to go and find the acceleration. I'm going to stay here and then switch to the tablet. So I derive that part using the tablet. Okay. So that was the coordinate system. And for the velocity, we got VB. So technically, this is point A. This is point B. We got VB equals VA plus omega cross RB respect to A. Which omega is this? This is the omega of the whole rigid body. Remember, each point has its own velocity, right? If you pick this point C, it has its own velocity. Point D has its own velocity. But for omega, there's just one omega for the entire rigid body. Sometimes people, I have seen this frequently, people write like VAB. There's no VAB. V is either for A or for B because it's a single point. But omega is for AB because the whole link rotates together. Okay. Now to find acceleration, we need to take the time derivative. Let's say I call this equation a star. Time derivative of equation star, which means I'm going to get dVB dt equals dVA dt plus d dt of omega plus RB respect to A. Right? What is dVB dt? This is going to be AB. This is going to be AA. Now, the derivative of this, again, you have like a product of two variables. You're going to get d omega dt plus RB respect to A plus omega cross drba dt. Right? We have done this before. You take the derivative of this, first times second, then first time derivative of second, like that. Any question? Now, what is the time derivative of omega? What is the time derivative of omega? Come on, guys.
Alpha.
Alpha as a vector. What is time derivative of this guy? That's tricky, huh? You remember how we started here? If we go back like a couple of mistakes, you had like drb dt is equal to dra dt plus drb respect to a we started from here, right? And we ended up that the derivative of this is this guy. Isn't this and this the same? drba dt, right? You guys follow? We already found the derivative of that. So if that's the case, we're going to go here. This is going to be this. It's going to be omega cross RB respect to A. The same thing we had here. Right? You guys follow? So, and we have seen before omega cross R, you can simplify it as minus omega square RB respect to A. You can use this equation too. Now, if you remember for rotation about fixed point, we call this as tangential acceleration. And we call this as normal acceleration, right? Now, technically, this is relative tangential acceleration, and this is relative normal acceleration, which means if you're sitting at A, this is the normal tangential acceleration, and this is the normal acceleration you see, right? Because remember, from perspective of A, B has pure rotation. So you're going to have tangential and normal acceleration. Any question? And this is vector analysis. That means you have to find alpha, omega, R, all of them as vectors, add them together. They have I and J and K components. Do the cross product and simplify and solve the problem, right? Any question about this derivation? Okay. You don't usually memorize the derivations. We just use the final equation and that is fine. But I sometimes, if the derivation is short, I show you how things are obtained so you know the concepts behind them. Now, in the next slide, practically what I did on the tablet, we're going to do the same. This is the time derivative. This is going to give you this part and this part. We separate them. It looks like rotation about fixed point, but in XY prime coordinate system, which is not technically fixed point. This is point A. But if you sit on A, you do not feel the motion of A. All you see is this rotational motion of B about A. Any question? Okay. So, and this is again considering this part is the tangential relative acceleration. This part is the normal relative acceleration. Because the relative motion of B respect to A looks like rotation. Any question? We're going to have some examples to solve. Let me, what time is it? We have 20 minutes. We may be able to go some, we may not be able to finish this completely, but that's okay. The problem says this wheel, and now you see how we use those relative motion stuff. This wheel rotates with an angular velocity of 8 radian per second. And we want to find the acceleration of this color A going back and forth. So practically, we have one rigid body, and another rigid body, right? Rotation only, translation only, AB has general motion. Because B is on the disk that we have, or the wheel that we have the information about, and A is something that we are looking for this information, we're going to consider the rigid body AB, which has the general motion, and write those equations, okay? Then let me just give you a minute to get this information, and I'm going to do the same. So This is how the problem looks like. Let me go to the tablet. So the slider, let me just write down the numbers. This radius, let's call it R. R is 0.15 meter. If I call this L, AB, LAB is 0.5 meter. This angle, they call it phi. And this angle, they call it theta. At this particular moment, theta is 30 degree and phi is 60 degree. And you have the disk and link AB and the color, and omega goes this way. And omega is 8 radian per second. Now I want you guys to pay attention to this, please, for a second. As I said, and I'm going to write it here, the wheel has rotation about a fixed point, which is 0.0. Right? Color A has linear translation. So this is one object, this is the second object. Link AB has a general motion. Right? Which means if you want to use the vector analysis, I have to consider 2 points on the link AB that helps me to solve the problem. Which 2 points you guys suggest? Remember, we are talking about link AB, right? If I want to pick 2 points and write the equations we derived in previous slides, what do you suggest the 2 points should be? Come on, guys, say something. Link point B, remember, these are pin joints, right? So technically point B is a pin that is a part of wheel, the blue wheel, and also the part of the blank link AB. Point A is a pin that goes through the link AB and also through the color, the green color, right? So it's a part of both. So if I pick link AB and I pick the 2 points A and B, I can write VA equals VB plus omega AB cross RA respect to B. Right? This looks like, and please pay attention here for a second. This looks like I put my moving coordinate system like x prime and y prime on B. And it moves with A. So if that's the case, what would be this vector A respect to B? That vector should look like this, going from A to B. This is going to be a relative vector, right? Our A respect to B goes from B to A. Is this correct? Now, because these are all vectors, I'm going to have to get the vector form of it. VA, what kind of motion A has? You know what? Let me get rid of these things. I'm going to use a red color. Hopefully, I can make it a little thicker so it can show you what our A respect to B is. Oops. This is our A respect to B. That's too thick. Okay. Right? Now, what kind of motion A has? Guys, these are simple questions. Just answer them. Don't hesitate. You may be wrong. That's okay. I want this communication. So first of all, you don't fall asleep. And second, I don't fall asleep. And then I'm sure you follow the steps. What kind of motion A has?
Translation.
Translation. So if translation, its velocity will be horizontal. Now we are in vector analysis, right? So I'm going to have a fixed XY coordinate system. This is my X, this is my Y, right? If this is the fixed coordinate system and this is VA, it's going to be positive, right? And by the way, because we are looking for velocity acceleration of A, I don't know if it goes to right or left. Sometimes the mechanism shows you how it moves. Sometimes it's not. I suppose VA goes to the right. Do I know its magnitude? No, because it's an unknown. So if I run it right, VA as a vector is going to be the value VA times I. Right? Now, how about VB? What kind of motion B has? Aaron, what kind of motion B has?
It has a bit vertical and a little bit horizontal.
Yeah, but what kind of motion in terms of rotation, translation, general motion?
Oh, rotation.
Rotation about fixed point, right? So B
Yes.
technically rotates about fixed point. So if I want to find VB, it's going to be omega of real or this. Let's just put omega this cross RB. And if I want to get RB, this is technically RB, right? This is going to be RB. Now, as a vector, RB is going to have X and Y component. If this is theta, how I can get RB? And by the way, first let's go with omega. Does omega go positive or negative? K, in terms of right-hand rule and stuff. If this is my X and Y, K comes out of plane toward me. So if that's the case, this omega shows positive omega K or negative omega K. Andrew, you tell me. You guys don't answer, I'm going to have to call. Use your right-hand rule. Tell me if omega is positive or negative. Andrew, do you hear us? I think he's busy with something else. Okay. Colin, how about you?
Would it be negative?
Negative, because you see, if I put my hands like this toward the omega, my thumb goes toward the plane, so it's going to be negative. So this is going to be minus omega d k cross RB. RB has a negative X and positive Y component, which means if the length of that vector is R, it's going to be minus R cosine theta I plus R sine theta J. And I'm going to do this cross product. So VB is going to be K times I, which gives you J. You're going to get R omega D cosine theta J minus R omega D sine theta I, which if simplified is going to be R omega D sine theta I plus R omega D cosine theta J. Okay, I got VA as a vector. I got VB as a vector. Now I'm going to go to find this term. Okay. So omega AB cross RA respect to B. If this rotates this way, omega AB could be this way or that way. It's hard to predict, right? And omega AB is an unknown value. So how about if I just suppose omega AB is positive? If I get a positive number, I am right. If I get a negative number, it's other way, right? So with this direction I have, omega AB is positive. So it's going to be omega AB K cross RB respect to A. Look at this big red vector. If I divide it into X and Y, let me get rid of some of this information that we don't need here. This is going to be its X component. This is going to be its Y component. Both of them are positive, and I'm going to use this angle phi. So X is going to be cosine phi, Y is going to be sine phi. The length of the vector is LAB, so I'm going to get LAB cosine phi I plus LAB sine phi J, right? Yeah. And if I do this cross product, it's going to be K times I is going to give you J. So omega AB, LAB cosine phi J. K times J is minus I minus omega AB LAB sine phi I. So this is the third term. Any question about finding these three terms? You're good? So technically, VA was just horizontal. I even didn't have to do anything. For VB and omega cross RAB, I had to do the cross product to find the vectors. Now that I have the three vectors, what is the next step? The next step is to substitute these values. Remember, we started with this equation. I found this, and this. So I'm going to substitute this guy. Oops. I'm going to substitute this guy, and this guy into top equation, right? Let's see what happens. If we do that, on the left-hand side, we have VA, which is VA times I. On the right-hand side, we have VB, which is this guy, R omega D sine theta I plus R omega D cosine theta J. And I'm going to add the final term, omega AB cross RAB, which is this guy, minus omega AB LAB sine phi I plus omega AB LAB cosine phi J. I put I first, J second. Okay, this is my final equation. Now you guys tell me how many unknowns we have in this equation. The problem asks for velocity acceleration of A and angular velocity acceleration omega A alpha AB, omega AB alpha AB, right? Let me see. The problem says determine the acceleration of A just for acceleration. So to find acceleration, we have to go with velocity first always, right? So the unknowns are VA and omega AB. Two unknowns. One equation, how we're going to solve this? Any suggestion? Let's call this equation as a star. Okay. Isn't it a vector equation? Go ahead.
We set up VA to be in terms of WAB. So like how to convert velocity to angular velocity. We substitute that in.
No, because you see, this is the equation I have. What you say is like going absolute motion analysis, relate, no, because you don't mix two methods, right? But look at here, star is a vector equation, right? Can I separate I and J components? Remember vector equations, I separate, J separate, K separate, right? You always do that. If that's the case, I'm going to separate I components and J components. On the left-hand side, you have only VA for I. On the right-hand side, this is I. And this is I. For the J side, remember, look at here, left-hand side, I don't have any J component, so it's going to be 0. On the right-hand side, so 0 equals, this is J component, and this is J component. Right? Now we have two equations to unknowns to solve it. Okay? Is it okay we spend a couple of more minutes to finish this part? Okay. Now, if I use the second equation, let's just call them equation 1 and 2. If I use equation 2, omega AB is going to be minus R omega D cosine theta over LAB cosine phi. And you will substitute the values 0.15. Let me see what are the other numbers. Times 8 times cosine 30 divided by 0.5 times cosine 60. Cosine times 8 times 0.15 divided by 0.5 and divided by cosine 60. So your omega AB is going to be minus 4.157 radian per second. What minus means here? Oh, we couldn't hear you, Aaron.
That's going backwards.
Yes, you know, we suppose omega is positive. Now we get it negative. That means goes backward. The way I thought omega is going to be is not the case. So that's okay. Now we have omega. We're going to go to equation 1 and get VA. I just substitute 0.15 times 8 times sine 30 minus 4.157 times 0.5 times sine 60. And if you do that, and minus becomes positive, so VA, I think you should get 2.4 meter per second. And is positive, which means the direction we chose was right. Any question about this problem? So there's a lot of calculations, right? We're going to simplify some of that as you get a little more experience, right? But it's quite straightforward. You get your equation set up. Let's go back here and repeat quickly. I wrote my equation. Okay, it's important to find which links to choose, and considering this is the output, this is the input, it's quite clear you have to go with link AB because that's the only link or rigid body with general motion. So you set up your equation, then you go find vectors one by one. right? This is just a straightforward omega cross R, you get it done. This is a straightforward. If you get your omega and RAB, just do the cross product. So it's kind of looks lengthy, but there's no trick involved in it. You can write a recipe, just follow one by one. Absolute motion analysis, you have to understand how to create the geometry. This one is just, as I said, straightforward, right? Any question? Now, Callie, can you do one of this as a quiz next time?
I think that would require a lot more practice.
Exactly. This is kind of because time derivatives, you had done it before. For r theta, we had done it. For constraint motion, we had done it. It was kind of more, when you set up the geometry, the rest is kind of easy. This is kind of new in terms of i's and j's and r omegas and r alphas and all of that. So you need to practice maybe a couple of more. So we're going to do a couple of more and we'll see how far we go. Okay. So thank you very much. I'm going to stop it here. Next time we continue this problem with acceleration part. Okay. So we're not done with this. We're going to go with acceleration. Okay. Any question or comment? Did you guys enjoy the lecture? Some of you, I think, were kind of sleepy in the midway, but if you fall asleep or get disconnected, now jokes aside, if you get disconnected or lose attention for any reason, I understand that sitting behind this, you know, your laptop or a screen or whatever you use, it's kind of boring and kind of you lose concentration. Sometimes you check your emails, sometimes you do other stuff. If that happens during the lecture, I'm going to post a video. You can go and get to that point that you kind of didn't follow completely. Watch the video again. If you have questions, let me know. Okay. Thank you very much. And I see you on Friday. Bye. So if you guys leave, I need to talk to one student. So let me see. People even don't sit here, I guess. They just turn on the things and go.
Okay, so I saw that the finals week was the week of the 24th, right?
The final week. Yes, it's going to be, our exam is going to be 28th of July.
The 28th, that Friday.
Yeah, because it's the last day of, you see, that's the rule by the university, that they want to have the exam on the last for the summer course, because you know that spring, fall, they have the exam set up certain days, certain locations. But for the summer courses, it's in the location of the class, which in our case is online and is in the on the last day. Now, what is wrong with the last day?
Well, so I'm going out of town on vacation the 24th. I'm driving to California, but any other day I'd be able to make it work, but the 28th is the day of my sister's wedding.
Okay, and what time is the wedding?
Early in the morning.
Which means like noontime here around. Okay.
Yeah. I need to double check.
You know that I don't think wedding is one of the excuses the university accepts, because it's usually emergency stuff. But I understand your sister doesn't have wedding like every week, is like once in a lifetime. So remind me the week before, like 18, 19, 20th or something, even the Friday before the final exam. Remind me to see how we can set that up, because I cannot give you the exam the week before because we're still covering concepts.
Yeah.
Right. I might be able to give you the exam like Thursday, the day before. Is that okay? Huh?
Yeah, like any other time, I could do it in the hotel or whatever,
Yeah.
just to make it work.
If
It's
we
just
do it that way, here's how it goes. Your exam is likely different from the rest of the class because I cannot give you the same thing and give the next day, you know, the idea.
Yeah,
And usually it's not intentional, but usually, and I talk to some of my colleagues, it's same with everybody. The makeup exams might be slightly more difficult.
okay,
Because you don't want to make it easier. It's hard to make it identical. You know, maybe one problem might be a little more challenging, but it's going to be still within the same thing. And I hate to do this because it's extra work for me,
Mm.
but that's not the case. Then the main thing is to make it fair and balanced. That's really difficult. You know, to create two exams, which looks identical, but they're not, you get my point. They
Yeah.
have to be very similar, but not identical, covering the same concepts, but not the exact same concepts. So it's kind of complicated, right? But for these things, I make an exception. Just remind me the week before,
okay.
so we can plan for it. And I suppose Monday and Wednesday of last week, you will be in the class, right?
Yeah, I'll try to tune in wherever I'm at, even if it's
Okay,
just on
and
my phone.
then we can even discuss the time the Wednesday before Thursday,
Okay.
right? What time is it? The way it works is this. I'm going to send you an email for the test, right?
Mhm.
From the time I send the email, your 75 minutes, sorry, for final is 100 minutes. Your
Okay.
100 minutes starts plus 10 minutes of scanning stuff. So you have to submit it in 110 minutes. Because
Okay.
you are the only person, I cannot make extras. So if you do not submit in 110 minutes, you practically get 0.
Yeah.
I may do it with the rest of class too, because I don't want you guys use that 10 minutes for, you know, solving and then you fall behind. This always, oh, my internet doesn't work, my submission doesn't work. 10 minutes is good enough to take care of that. For you just to email it to me, it's easier. And all the times are recorded so we know what is what, okay?
Okay.
We make it that way. And yeah, just remind me the week before, and then we set the time, because I cannot plan my Thursday of, you know, 3 weeks ahead from now,
Yeah.
to be honest with you, because, you know, we have stuff to do at home. My son goes to the soccer camp and the stuff. I might be even out of town myself, hopefully not. I try to stay at home for the course because it's hard to guarantee, you know, signals if you are in a hotel or vacation. So that's not, I'm gonna have to be at home anyway. But make sure that I'm in a place that I can send you the email for the exam. Is it a
Okay.
good plan?
Yep, I'll remind you in like 2 weeks before
Yeah.
the week before finals.
Okay.
I appreciate the help. I know it's unfortunate that timing.
You know, as I said, let me tell you this. I had students who said, hey, I'm turning 21. Next week, I'm going to be out of town. I'm going to drink, can't come to class. So listen, you do what you do, but that's not an excuse I can accept, right?
Yeah.
Usually it's like illnesses and hospital, you know, things, and, you know, God forbid, you know, family funeral. Those are things I think university accepts easily.
Mm.
Now I'm going to add, you know, the happy moments to it, because we don't have to just suffer to make it like this. So I try to make it work this way, and hopefully it works.
All right.
Okay. Take
All
care.
right.
Bye.
I'll see you Friday. Thanks for the help.
See you.